This video will take a look at introducing you to what are referred to as sinusoidal relations. We're going to go through some key vocabulary that will be necessary to describe the appearance of these graphs, as well as the general shape that these graphs will take on. They're primarily used to describe sine and cosine functions that we've already studied a little bit in our trigonometry studies in both grade 11 and already in this course. So first two terms that I want to introduce you to are what are referred to as periodic. So this graph down here, if we look at it, is considered periodic. Now the reason it's periodic is because it says the dependent, which are the y variables, take on the same set of values over and over. So if you look at the y values, once you get to here, there somewhere, the pattern just repeats itself again, and they take on the same y values again. And it's the same pattern on the y scale over and over as the x's, which are the independents, are changing. That's referred to as periodic behavior. If you go down here and look at sinusoidal function, so it's periodic. It has to be periodic, and then it will also take on the pattern of a nice smooth wave, like you see here. So it won't have those jagged corners and edges to it. It will be a nice smooth wave. Looking at these three graphs down at the bottom here is our sample. So if you look at this first one, that is definitely sinusoidal because it's periodic. The y values repeat themselves over and over, and it has a nice wave pattern to it. This one is periodic because it does repeat the same pattern over and over on the y scale. The problem being that it's not that nice wave pattern, so it's not sinusoidal, but it is periodic. This one will be neither. Now, sometimes you say, oh, it's a wave. Well, in order for it to be a sinusoidal wave, it has to have the same y values over and over. You can see here that the y values are not the same. They don't go as high each time. So yes, it is a wave pattern, but it's not a sinusoidal wave. So those are two key terms, sinusoidal and periodic. So the next thing we want to look at is how to determine what these graphs look like. So for most of you, these are completely new graphs. You have no idea what they look like. So we're just going to go through and see if we can kind of plot them out the way we would any graph and just kind of get a general idea of what the shape of these graphs will be. And then once we do that, we'll kind of speed up the process and show you some little quick shortcuts as to how we're going to graph these. But that's the first focus that we're going to have is how to graph both sine and cosine functions. And we're going to start with the sine function. So you see here I've got y equals sine of theta. So theta, which is sometimes interchanged for theta or x, some variable, whatever. And then over here, you have your y values, which are here. So I've got a scale set up. You can see it's in 30-degree increments. So I'm going by 30s every time. And what we're going to do is plug each of those in for theta, find the sine of that angle, and we're going to fill that number in here, and that'll give us the y value, because it says up here, the y value is equal to the sine of whatever theta is. And these numbers that we've already identified, those are the theta values. Now, we can do it out by hand. It would take us a little bit longer. So what we're going to do is we're going to rely on Desmos, which hopefully all of you are familiar with. We've used it throughout the year. And I've got it all opened up and ready to go here. So the first thing I would suggest that we do is set up our graph, our scale. So we're going to want to go over to the wrench icon right here. I'm going to select that. And the first thing I'm going to do is make sure I'm in degrees, which I am. I'm going to take the x-axis, and I'm going to go from -90 up to 300. Actually, let's go a little bit further than that. Let's go to 450 degrees. Step just means what do you want your increment to be? So you can see I set it at 30, which means I'm going to go in blocks of 30, which I have here. The y-axis, you don't know this yet, but we're not going to need it to go any higher than 1 or lower than -1 for now. So we're going to set it at -2 as our smallest number. And we're going to set our biggest number at 2. And we'll just leave it as it is. It's going up by halves, which is fine. Okay, so I'm going to go over here now, and I'm going to type in the function y equals sine of x, and it kind of gets ahead of us and gives us the graph, what it looks like. Let's suppose we didn't know what it looked like. So here's a way that we can do it. So I'm going to click the little gear icon here, and I'm going to choose convert to table. Now I want my table to match the one that we had on our smart file. If you remember, it went by 30s. It started at 0, so I'm going to start at 0. Now when I put an angle in here, it's going to plot the ordered pair up on our graph. Right here, you're going to see the dots start appearing that match up with this table of values over here. So first one I'm going to type in, we're going to start at 0. And the sine of 0 is 0. So we're going to have a dot at 0, 0. Next one we're going to go is 30. Not negative 30, sorry. Just 30. The sine of 30 is 0.5. The sine, the next one is going to be 60. You can see the dots appearing over here on the graph as we're putting these in. These dots are showing up. So the sine of 30 was a half. The sine of 60 was 0.86. As some of you may recall, that's actually radical 3 divided by 2. 60 is one of our special angles, and the sine of 60 degrees was square root 3 divided by 2. Okay, so we're just going to speed this up, and I'm going to fill in all the rest of them. You're going to watch the dots and see the pattern that it makes. So I get 60, 90, 90, sorry, 60, 90, 120. And now once it picks up on your pattern, you can just hit enter, and it'll just keep the pattern going. So now it's just going to keep putting them in groups 30 or increments of 30, and we're going to keep going. See the pattern developing on our graph. I'm going to go a couple places past it, and you can see the pattern that it took on, and you can hopefully now make the connection why in that first slide we had a pattern called a sinusoidal relation. If you remember what it looked like, I'm just going to go up here now. And put my function back in, y equals sine of x. There's a nice picture with the dots all connected. And this is what is known as the graph of y equals sine of x, or sine of theta. So it is a periodic function, and it is sinusoidal. Key things to notice: the highest point it ever reaches is 1. The lowest number it ever reaches is -1. If you think of that, that shouldn't surprise you, because if you remember when we did this, we did it on the unit circle, where we used our 0, 1, 1, 0 ordered pairs, and you never got a sine value that was ever any more than 1 or ever any lower than -1. Another way to think of it is that the sine of an angle is the opposite divided by the hypotenuse. The hypotenuse is always going to be bigger than the opposite side. So when you divide those two into a ratio, you're always going to get a number that's either less than 1 or more than -1. But it's never going to be a number that's more than +1 or less than a -1. I said that backwards. So it's smaller than 1, greater than -1. It starts the pattern at 0. If you notice here, let's get my pointer. So it's at 0, 0. That's important. The graph of sine x starts at 0, 0. And it goes up first, hits its high point at 1. And notice it's at 90 degrees, which is one of our quadrantals. It then makes its way down here to 180, back at 0, right back up, and then it hits 360. Now you can't see it, but if this pattern continued, think about it on the unit circle. It's like spinning a terminal arm around in a circle. You go from 0, you get back to 360. Well, if you were to continue that pattern, it's just going to plot the same numbers over again, and you're going to repeat that pattern as we move up and follow the graph this way. So that's why it's periodic, the behavior. It's just going to keep repeating the same pattern over and over. So you notice also that it starts the pattern at 0, and it's finished the pattern when we get to 360 degrees. That'll be important here in a couple of minutes when I start talking about some of these descriptors we're going to use to describe the graph. If I'm not going to go through the whole process, but we could go through the whole process of plotting every 30 degrees, like we just did, and do it for cosine. I'm just going to type in cosine x and get you to have a look at it. So here's cos of x. Now notice some people may look and say, oh, it's the same thing. It's close, but it's not quite the same thing. It's the same type of pattern. The biggest difference is a cosine graph, because the cosine of 0 is not 0. The cosine of 0 is actually 1. So at 0, this graph's up at 1. And then if you follow the pattern through, cosine of 90 is 0. The cosine of 180 is -1. The cosine of 270 is 0. And then the cosine of 360 degrees is back up at 1. So it's the same type of pattern, except this time at 0, it starts at 1, works its way down until it hits its lowest point, which is at -1, and then it's going to work its way back up to its highest point at 360. And then, of course, from here moving forward, it would repeat itself, get that same pattern again. If you went back this other way, you'd get that same wave pattern again as well. So this one, same thing. Highest number it ever reaches is 1. Lowest number it ever reaches is -1. Pattern starts at 0. The pattern ends at 0. At 360. So it takes 360 degrees to complete that full pattern. And of course, this could be interchanged for radians. The only difference would be the starting point would be 0, and the end point would not be 360 anymore. It would be 2 pi. And if you wanted to use radians, you could do that. You'd have to go back up here to your settings. You remember in the beginning, one of the options was radians. You could do that, and you would just pick 0 as your start, 2 pi as your end on your x scale, have your step be 30 degrees, so pi over 6, and it would scale it out and put the pi's in here for you instead. So that is what a sine wave and a cosine function look like. Now, I know this is y equals cosine of x. It is still referred to as a sinusoidal relation. So both sine and cosine are what we're going to refer to as sinusoidal relations. Okay, so let's go back to our smart notes and pick up in there. All right, so this is basically what I just went through and talked about. So rather than do it by hand, we use technology to help us out. So here's the terms that are important that we're going to have to become familiar with. So the first one is what's referred to as the period. So the period of a sinusoidal relation is the interval required to make one full pattern. So this is the graph of sine x because it starts at 0. It goes up to its highest point, down to its lowest point, and now I've changed the numbers on here, so it's still a sinusoidal pattern. It's not your regular sine x. It's got some transformations to it. But you can see it started its pattern at 0. It finished the pattern, or the wave, one full cycle. We call that a full cycle. It took 12 seconds. So we would say that this graph has a period that would equal 12. Now, whatever the units are. This one says 12 seconds. We'll just say that it's 12 for the sake of argument for now. Whereas if you remember the graph we had for sine and cosine, we said they started at 0. This number wasn't 12, it was 360. We would have said that graph had a period of 360 degrees because that's what it took on the horizontal scale to make one full pattern. That's referred to as the period. So that's the first term I would want you to be able to use as we discuss these. Second one is what is referred to as the sinusoidal axis. So these waves, what we're eventually going to get to is we're going to move them up, down, left, right. We're going to stretch them vertically, horizontally. We're going to use all the transformations we used in Unit 1. So if we look at this graph, the sinusoidal axis is the dotted purple line that I put that's right here. That purple line is called the sinusoidal axis. It's always going to be a horizontal line, running side to side. And it's always going to be in the middle of the wave. So if you looked at this wave, its highest point was 2. Its lowest point was -4, which is a total distance vertically from top to bottom. It was 6 units wide. So half of that would be 3, which means you go either from the top and go down 3, or go from the bottom and go up 3, and that'll put you right in the middle of the wave. So if I'm from here, the distance from here to here is, right, from there to there is 3. And if I go from the sinusoidal axis down to the lowest possible point, it's going to be the same distance. Now, if you say, oh, I think this is the sinusoidal axis right here. I said, well, no, it's only from there to there is only 2, but from there to there would be 4. So that's not the middle. That's how you know you're not at the sinusoidal axis. It's important that you always describe these properly. Don't just say the sinusoidal axis is -1. That doesn't describe a horizontal line. So the sinusoidal axis you'll see here is y equals -1. It's always going to be y equals the number that it's cutting through on the y scale. So that's the sinusoidal axis. Okay, so that slide, 2 terms, period and sinusoidal axis. Next term, amplitude. Sorry. Amplitude is a term that refers to how far is it from the sinusoidal axis up to that high or low point. So in this graph, our sinusoidal axis, which if I look here, it is at y equals -1. So there's your sinusoidal axis. So what's referred to as the amplitude, which is also, I think, a physics term that you'll use when you study waves, is how far is it from the middle up to the high point. Well, we said that it was, we'd already talked about this, it's 3. So this wave has an amplitude of 3. There's a formula, there's a way you can calculate it, and it is simply this. The top number, so the max number, take away the smallest number, and then you just take half of it. So for example, on this one, the biggest number was 2. The lowest number was -4. So if I had gone here and said, okay, well, the amplitude is 2, subtract a -4, and then I'm going to divide that by 2. Well, 6 divided by 2, it would have given me 3. Now, some may argue you're really overcomplicating things. However, some people are kind of formula driven and they like to have a formula. So that is a way you can actually calculate the amplitude. But I think most of you are going to be able to do just look at a wave and tell me the amplitude. So those are the 3 main terms I need you to be able to identify: the amplitude, the period, and the sinusoidal axis. So if we just summarize what we talked about here, here's the regular old sine wave. Let's look at it and see if we can identify those 3 terms. So if I look at this graph and say, what is the period? Well, let's say it starts here, follow it through. There's one full wave. It started at 0, ended at 360. Now, they're not always going to start at 0 and end at a nice number, but in this one, it's nice and easy to get it started. So this one would have a period of 360 degrees. The sinusoidal axis, well, it's the actual x-axis right here, because from here up to here is 1, and from that axis down to the lowest point is also 1. So it's already in the middle. Well, that line is just y equals 0. So your sinusoidal axis is just the line y equals 0. And the amplitude, which refers to how far is it from the middle, or your sinusoidal axis, to either the low point or the high point, or in this case, that distance would just be 1 unit. Amplitude is always positive because it's a distance. So even if your whole wave was down below the x-axis down in negative numbers, your amplitude would always be a positive number. Okay, so that's those 3 key terms. We've already looked at cosine. So remember cosine, the difference is it starts at 0, it's up at 1 rather than going through the origin 0, 0. I've got the 2 summarized here in the next slide. Okay, so here's our 2 basic functions that we need to make ourselves familiar with and their patterns. So you'll see I've kind of really chopped it down now, and we're only going to use just our quadrantal angles. So basically when we plot these, we're just going to rely on these 5 key points over here, which are, if you think of the unit circle, if you remember what the heck you're talking about, the unit circle, you went 0, 90, 180, 270, and then back here is at 360. So technically 0 and 360, we're talking about the same spot. If you work your way around the pattern, so 0 is at 0, 90 is at 1. 90 is at 1. 180, the y value is 0. 270, the y value is -1. And then 360, the y value is back at 0. So the period, as we've already identified, is 360. That's there. The amplitude from the middle to the lower, the high, is 1. Sinusoidal axis is y equals 0. Now the domain of these graphs, which is along here, unless we're told different, we're going to assume that this wave can continue indefinitely in both directions, which means the angles along here could be any number you ever want them to be, won't matter. And the range, which is the y values, well, they're going to oscillate, jump back and forth between a high number of 1 and a low number of -1. So you're going to write it as -1 is less than or equal to y, which is less than or equal to 1. And we looked at last unit, we can now use this notation as well, bracket notation. So -1, comma, 1. That would also cover that interval. If you look at the cosine, it's pretty much all the exact same information. In fact, this stuff is all exactly the same. The only thing that's different are the numbers down here. So if we look at this, at 0, the wave's up at 1 rather than 0, 0. At 90, because the cosine of 90, cosine, remember, goes with x values. And if you think about working your way around the unit circle like we did before, right? So this point here is 1, 0. So the x is 1. So at 0, cosine is 1. Just to hopefully try and jar your memories a little bit. So as I work my way and plot those 5 key points, 90, 180, 270, and 360, those would be their corresponding cosine values, and you'll get that nice wave pattern. Now, we'll let you use just these 5 points and not make you use, every 30 or every 15 degrees or something, provided you're not going to take these. Here's what students will do wrong. They'll put their 3 or their 5 dots, one there, another one here, another one here, and another one here, and then they'll draw a graph that looks kind of like this. Well, that's a bad line. But they'll basically have straight lines that go to here, and then another straight line that goes out to here, and their graph will end up kind of looking more like an absolute value graph than an actual sinusoidal wave. So if you're going to use 5 points, you got to make sure that you draw your graph to make that nice wave pattern, not this straight line pattern like this one did. I don't want to do that. All right, so now, just to jar your memory, so recall from our studies with quadratics, if we put a number here, that was called a reflection. It flipped the graph over if you put it out in front. If we put a number here, that was a vertical stretch. Just think of our first unit that we did in this course on functions, where we went with something like this, h of x equals a f b, let's say x plus c, and then, I don't know, minus d. So depending on where the number is situated in the function, we're supposed to now know from our first unit on what the visual effect is going to be on that particular graph, whatever the base graph is. So in this case, the base graph was y equals x squared, because it was just a parabola. We can see that it's going to get turned upside down. It's going to get stretched by a vertical factor of 2. This is going to move it to the right 3 units, and this is going to move it vertically up 4. So generally speaking, down here, the number in front is a reflection in the x-axis. That'll flip it over in the x-axis. This one is a reflection in the y-axis. We don't usually reflect these trig graphs in the y-axis, but you could run into it somewhere. This will be the horizontal stretch factor. This would be your horizontal, it's called translation, so that'll move your graph left and right. And this would be your vertical translation that would move your graph up and down. So if we go to this one and we apply these now, let's go down here to our trig graph. So here's an example of a trig function. So the base function in this case, I think we would all agree, the base function would be y equals sine of theta. And we know from our past slides that it's that basic pattern. Start at 0, end at 360, roughly looks like that. Well, putting this negative here is going to reflect the graph in the x-axis. So it's going to take this wave, and now it's going to make it go down, because these are going to come down here, and these are going to go up here. It's going to go down first and up this way if it's negative. The 2 is going to stretch it vertically by a factor of 2. So now instead of going up to 1 and down to -1, it's going to stretch everything this way and this way. So it's going to go up to, it's going to double this number. So now it's going to go up to 2 and down to -2. And again, I'm doing this really quickly. We're going to get lots of chance to practice this in a moment. I'm just trying to draw a connection to our first unit on functions and see how this is all tying back together. The 3 here, which would correspond with this number here, and if you can remember from functions, this was a horizontal stretch. And the factor in this one, if you remember, was always the reciprocal. So it would be 1 over b, the width of what it used to be horizontally. Well, if I go to this graph, that's going to tell me then that this graph's going to be 1/3 the width of what it used to be. Well, we know that it used to be 360 degrees wide. It's now going to make the same pattern in 1/3 of what it used to. So it's now going to adjust what's called the period. It's going to make the period adjust from 360 down to 120. So that's going to have so this one we said is going to affect the amplitude. This number is going to affect the period. Now, this number is going to move to the right. Remember, this one's always the opposite in here, so it's going to go to the right 60 degrees. So on your scale, it would take the graph and just physically slide it to the right 60 degrees. And then the -1 at the end, based on our knowledge of function transformations, was going to take this graph after we do, remember the order, it's always R, S, T. So reflections, stretches, and then translations is always last. So once I've reflected it and then stretched it up and down and compressed it, made it 1/3 the width, then I take the graph and slide it right 60 and down 1. And that's kind of our goal here over the next set of videos, is to figure out how to take something like this and have you folks draw. And the good news is, as complicated as it may seem right now, this is always something that students generally pick up very quickly and don't have a whole lot of trouble doing. Oops. I just want to go back to Desmos for a second before we wrap up this first video. And so we'll use cosine as an example. So let's, leaving cosine on there, just to show you, I'm going to put in here y equals 2 cosine x. And what that should do is make this graph stretch vertically by a factor of 2. So notice what happened. It's the exact same graph, except it went up to 2 and down to -2 instead of up to 1 and down to -1. So it adjusted the period. Or sorry, not the period. It adjusted the amplitude. The amplitude went from 1 to 2. Okay, so I'm going to now draw another graph. I'll leave, actually, let's get rid of that one. I don't want to get too much on the go here. Let's put the cosine, and I'm going to put a bracket here, of 2x. So putting a number here should make it half the width of what the original graph was. So this should now make a wave in 180 degrees instead of 360. Let's see if that works. So look at the red graph, and if we follow it out, it now starts its pattern here at 0, up at its high point, goes down, back up, finished, one wave. But look at where it's done now. Now it's done at 180 instead of 360. So by putting a 2 here, it made the same pattern in half the distance on this scale. So that affected what we refer to as the period. It had half the period. So if I get rid of that, and let's suppose I said, oh, I'd like to move this graph that I can see here 30 degrees to the left. Well, we know how to do that. We just put after our cosine function, put a bracket, x. Make it move left, I want to put a plus, let's say 30. And all of a sudden, our original graph, which was in black, has now shifted. So let me write on here, but if you look here, this high point, which was here, is now over here and has moved left 30 degrees. This point, which was here, is now over here. It moved left 30. So everything shifted left 30 degrees. And if I wanted to make it, let's say maybe that graph you can see there in red, say I'd like that graph to be moved down 1.5 units. So I'll just put subtract 1.5, and all of a sudden our wave has moved down vertically 1.5. The one that I didn't, let's just quickly look at a reflection. So if I had this graph, but I wanted it to be reflected, so watch what will happen. I'm going to put here out in front a negative cosine of x. So what that should do is the loop up here, so basically your positives will become negatives. Your negatives, because you're taking the negative of those numbers, they'll become the positives, and these will flip down here. So let's finish it out and see what it looks like. As we said, so basically these numbers flipped and went down here and became their corresponding negatives. These negatives were multiplied by negatives, so they became positive, and basically your graph got reflected or flipped across the x-axis. We'll look at the other one, which again, I said this one you don't use a whole lot, but we'll just look at it. So if I took this graph, cosine of negative x, and I graphed it, you may say, well, nothing happened. And that's true, nothing happened, because if you look at your graph at 60 degrees, so at 60 degrees, it was here, but if I reflect that across here, it's going to end up there, but there's already a point there already anyway. So imagine folding this graph across your y-axis. If you were to flip this whole graph across, it would end up right on top of this other one over here. I don't know if you can remember, I know it's been a long time now, but when we did our trig equations, do you remember if it was a cosine function and you had the cosine of 60 and you were going to do negative 60 would turn out to be your other angle? Well, the reason that 60 and negative 60 had the same value is because of this symmetry you have with cosine. Now watch, if I switch this to sine, that won't happen. So if I go up here and switch this to sine x, and then I change this to the sine of negative x, right, so this graph now, there's sine x. Well, 30 degrees, for example, when I flip it across, there's not a point already sitting there like there was with cosine. So when I put my sine function here, see how it folded across, but it's going to change the look of that pattern, whereas it doesn't with cosine. And that would be your horizontal reflection across the y-axis. All right, so that summarizes what the graph of sine x looks like and what the graph of cosine x looks like. It introduces you to the term periodic, sinusoidal, amplitude, period, sinusoidal axis, and then we looked quickly at how we could transform or move those graphs around according to what we already know in terms of our function unit that we studied in Unit 1. All right, so that will be the end of video 1 on sinusoidal relations.